As science delves deeper into the cellular mechanisms of aging, telomeres, the tiny protective caps at the ends of our chromosomes, have emerged as both powerful biomarkers and active participants in the aging process. These DNA protein structures serve as buffers that prevent our genetic material from unraveling or fusing together during cell division. Yet with every replication, telomeres grow slightly shorter. Eventually, they become so abbreviated that cells can no longer divide effectively, triggering a state of cellular senescence or programmed cell death. While this mechanism is essential for preventing uncontrolled cell growth, such as in cancer, it also plays a pivotal role in how fast we age. The shortening of telomeres is now understood to be far more than a curiosity of molecular biology. It is closely tied to the risk and onset of many age-related diseases, including cancer, cardiovascular disease, and immune dysfunction. Importantly, telomere length reflects biological age more accurately than chronological age. Two people born on the same day may have dramatically different telomere lengths and correspondingly different risks of disease, depending on their genetics, lifestyle, and exposures. One of the clearest associations in the field of aging is between shortened telomeres and cardiovascular disease. Large-scale studies have repeatedly shown that individuals with shorter telomeres are more likely to suffer from conditions such as coronary artery disease, hypertension, and heart failure. The mechanism is multifaceted. As vascular cells lose telomere length, their ability to repair arterial damage declines, leading to the buildup of plaque and arterial stiffness. Endothelial dysfunction becomes more common, contributing to blood pressure imbalances and impaired circulation. Essentially, the vascular system becomes biologically older, less responsive, and more vulnerable to stress. Cancer represents another key connection to telomere biology. On one hand, short telomeres serve as a protective mechanism by preventing excessive cell division, thus acting as a barrier to tumor formation. But on the other hand, when telomeres become critically short, they can cause genomic instability, leading to chromosomal fusions, mutations, and DNA damage. This instability can actually promote malignant transformation in certain contexts. Research has shown that individuals with significantly shortened telomeres in their white blood cells are at higher risk for several cancers, including lung, bladder, gastrointestinal, and hematological malignancies. This paradox illustrates that while telomere shortening is a defense against excessive replication, it may also create a fertile ground for errors that lead to cancer when the balance is disrupted. The immune system is especially sensitive to telomere dynamics. T cells, which are vital to immune response, must replicate rapidly in response to infections. However, with age and repeated activation, their telomeres shorten significantly. As a result, older adults often face immunosenescence, a state in which the immune system becomes sluggish, less capable of responding to new infections, and more prone to chronic inflammation. This impaired immune resilience makes the elderly more susceptible to everything from viral infections to cancer and autoimmune conditions. Indeed, studies show that people with shorter leukocyte telomeres are more likely to develop chronic inflammatory states, which not only degrade quality of life, but also promote the very diseases that telomeres are meant to help guard against. What makes this body of research even more promising is the growing understanding that telomere length is not fixed. While genetic factors do play a role, environmental and lifestyle factors strongly influence telomere attrition. Smoking, obesity, sedentary behavior, chronic psychological stress, and nutrient-poor diets all accelerate telomere shortening. In contrast, interventions such as physical activity, stress reduction, antioxidant-rich diets, adequate sleep, and certain micronutrient supplements, including vitamin D and omega-3 fatty acids, have been associated with longer telomeres or reduced shortening over time. This opens the door to a more optimistic view of aging, not as an inevitable decline, but as a process we can modulate. By protecting our telomeres, we may be able to extend not only lifespan but health span, the years we live free from major disease. Already, studies have shown that individuals with longer telomeres tend to live longer, healthier lives, with lower rates of heart attacks, strokes, and age-related cancers. Researchers are now exploring how telomere maintenance can be integrated into preventive medicine. Measuring telomere length may become part of routine health assessments in the future, offering insights into an individual's biological age and risks. More importantly, it may allow for personalized interventions, targeting those at greater risk with lifestyle changes and therapeutic strategies aimed at preserving telomere integrity. In sum, telomeres are far more than passive markers of time. They are dynamic structures at the center of aging biology, and their status reflects, and potentially influences, our vulnerability to many of the diseases we fear most. The connection between telomere shortening and chronic diseases like cancer, heart disease, and immune dysfunction is not just theoretical, it's backed by decades of molecular and epidemiological research. The encouraging news is that we are not powerless in the face of telomere erosion. Lifestyle choices, stress management, and nutritional strategies can help preserve these molecular guardians of cellular health. And as science continues to explore targeted therapies, we move closer to the possibility of not just delaying disease, but redefining the boundaries of healthy aging itself.